Okay, now that we know the definition of the indefinite integral and now that we know what antidifferentiation is about, we need to talk about methods how to find antiderivatives, and there are three primary methods to find antiderivatives: substitution, integration by parts, and partial fractions. And so that's what this presentation as well as the next two presentations will be about. Well, let's see what we've got. Symbolic integration, simply put, is about undoing derivatives. We've seen that. And that means we're given a function which is actually a derivative f prime, and we're supposed to find the original function f. But most functions cannot be obviously recognized as derivatives of other functions. In the first presentation, we've simply just written down differentiation rules backwards, and those were our integration rules. Well, how likely is it that you actually will run into a function that looks exactly like one of those 7 or 8 functions that we had on that slide in that previous presentation? It's not very likely. So basically, we need some more ideas about how to reverse differentiation rules to get more methods for symbolic integration. But the note here is that unlike differentiation, integration really is not a cut and dried process. The integration methods may not give you the solution right away. It won't be clear which method to use at first, hopefully only at first. And there even are functions such as the function e to negative x squared for which it can be proved that all symbolic integration methods fail, meaning there is no closed expression that gives the antiderivative of the function e to the minus x squared. So this is a fundamentally more challenging process than just computing derivatives, even though computing derivatives, as we've seen, can also get rather nasty. But not to worry, we'll get through this too. So let's see. Integration by substitution. The idea for integration by substitution is basically that we want to reverse the chain rule. Now, remember, the chain rule was that the derivative of a composition was the derivative of the outer function evaluated at the inner function times the derivative of the inner function. Well, recognizing functions as such chain rule derivatives, that sounds pretty hopeless, because that's an awful lot of stuff that just has to line up right, and even if it lines up right, we might not even be able to see it right. So let's take a step back and realize that compositions themselves are easier to detect. And then if we now substitute a single variable, say u, for the inner function g of x, then the problem should become easier. Well, and that's where I can say this is best demonstrated with an example. So let's take a look at our first example here. We want to find the indefinite integral of the function sine 4x. And well, we can find the antiderivative of sine of variable. We can find the antiderivative of sine of u. So if we just let u be equal to 4x, well, that would be nice, but we don't know how to integrate u with respect to x. What we do know, however, is that if u is equal to 4x, then du dx is equal to 4. And we can solve that for dx. dx becomes du over 4. And that means that the integral of sine 4x is the integral of sine u dx, and then dx becomes du over 4. A little special effect here, but basically that's the key to substitution. We change the dx into a du, and basically the rule of thumb is that you don't integrate u with respect to dx, you don't integrate x with respect to du. You always need to make sure in a substitution that all your variables in your integration are the same. You don't mix them up. Once we've got that, well, this is just 1/4 sine integral sine u du, and we know the antiderivative of the sine function is the negative cosine function, so this is 1/4 negative cosine u plus c. But we wanted to have our function, of course, in terms of x, so we replace the u again. So this is negative 1/4 cosine 4x plus c, and that supposedly is the answer. Well, this part over here, the separation of differentials, is something that can give some colleagues of mine, and rightly can give some colleagues of mine a little bit of a fit, because du dx was a compound symbol for the derivative in standard mathematics, let's call it that way. There really is no such thing as a differential that has meaning in and of itself. Well, now physicists have no trouble separating those differentials. They just consider them small differences in the output and in the input, and then it starts making a bit more sense. And actually, even in mathematics, there is a branch called non-standard analysis that shows that this really can be done. It's just that that is a very sophisticated branch of mathematics, and unless you want to be a mathematician in that area or you're interested in it, you probably aren't going to see it. So that means we ought to be careful here and justify this mnemonic way of executing substitution. And the first step in that direction is to make sure that we really got the example right, and that is something that I'll also be harping on in integration quite a bit. Whenever you solve an integral, that's a hard problem, it takes quite a bit of time, it's worth double checking. And well, how do you double check an integral? You take the derivative. Well, the derivative of negative 1/4 cosine 4x plus c is negative 1/4 times the derivative of cosine is negative sine, so you get negative sine of 4x times the 4, which is the derivative of the inside, and then of course the plus c, the derivative of that is 0, and when you simplify that you get sine 4x back. So at least for this example, this method worked out. Well, if this method only works for certain examples, then it's really not a mathematical method, and it turns out that integration by substitution does work in general, and here's why. The abstract theorem for integration by substitution is that if you've got a function that is defined on an interval, and if capital F prime is lowercase f and g is differentiable, then the integral of lowercase f of g of x times g prime of x dx is equal to capital F of g of x plus c. Well, what else would it be, right? That's just another one of those where you write down a differentiation formula backwards and you get an integration formula. But what does that have to do with the procedure that we've had on the previous slides here? Well, if we're looking at this, we realize that in our previous procedure, we said that the inner function, the g of x, we called that u, right? And so that occurs here as well as here. And then du dx is g prime of x, which means that du is g prime of x dx. So the du is here. And so our substitution on the previous slides replaced this integral with the integral of f of u du. We didn't quite say du is g prime dx. We said dx is du over g prime and then did some cancellations, but that's the same thing. Either way, the process replaced this with an integral f of u du. Then we solved that, and of course the integral of f of u du is just the antiderivative at u plus c, and then we substituted back, and so we ended up with that right-hand side. So even without non-standard analysis, even without the physical intuition that physicists use in amazing ways to solve integrals and to do mathematics that ultimately gives them correct predictions of nature, even without all that, we can at least acknowledge that this mnemonic way of doing substitutions does work. And that is certainly the main goal here. We want to solve those integrals. We want to solve them correctly with a method that reliably works, and that's what this is. And so with that being established, we can go to some examples. Compute the integral of x squared e to the x cubed. Well, that does look horrible, but remember that as soon as we identify a composition, and here it is, the x cubed is plugged into the exponential, we can try a substitution, and the substitution then would be x cubed. Du dx is 3x squared, we just take the derivative. We solve for dx, we get dx being du over 3x squared. Sure, no problem there. This one comes over, this one goes down. And now we realize that the integral of x squared e to the x cubed dx is equal to the integral x squared e to the u du over 3x squared. No special effect this time around. I'm violating sort of what I've said before, which is you don't mix x's and u's. Well, when it's more complicated, you have no choice, but basically what you have to make sure is that before you integrate, all the old variables cancel out. And that's what of course is happening here. This x squared cancels with this x squared, and so we end up with the integral e to the u du over 3, which is 1/3 integral e to the u du, and that's the stage that ultimately always is our target. We have everything in terms of u, and we can find the antiderivative, which is of course just 1/3 e to the u plus c, and then we back substitute, and this is 1/3 e to the x cubed plus c, and again, always make sure that you are right. Double checking means we take the derivative. The derivative of 1/3 e to the x cubed is 1/3 times e to the x cubed times the derivative of the exponent, which is the 3x squared. The plus c, of course, went away, and the 1/3 and the 3 cancel. We end up with x cubed e to the x cubed, which is what it should be. All right, what else do we have? That's not a composition now. Or is it? Well, let's see. This one is one, and that's the kind of thing where you have to be careful with substitution. Sometimes compositions are hidden. And if you divide by y squared plus 1, well, that basically means that you plug y squared plus 1 into the function 1 over x. And that's a composition. Another way to look at that is if you don't see an obvious composition, as a rule of thumb, you could try to substitute the denominator. So let's see what happens. The denominator is y squared plus 1. du dy is 2y, which means that dy is du over 2y, right? dy comes over, 2y is divided by. And notice I've snuck another thing in here, and that is whether our integration variable is y or x or z or whatever else, it doesn't matter. Substitution always works the same way. If our integration variable here is u, well, then we would need to something like a v or a w to do the substitution with, but it would all work the same way. Now let's get back to this one here. We have the integral of y over y squared plus 1 dy. That turns into the integral y over u du over 2y, and again, thankfully, we see that the y's cancel. 1/2 integral 1 over u du. Now, if that cancellation ever not works out, do not substitute, do not proceed. Something went wrong, and you may need a different method, a different substitution, or maybe even an entirely different method, such as integration by parts. But here in these examples, things do work out, and the integral of 1 over u is, of course, the ln of u. So you get 1/2 ln u plus c, and then we back substitute, and we get that the antiderivative is 1/2 ln y squared plus 1 plus c, and we can double check very easily that that works out, because the derivative of 1/2 ln y squared plus 1 plus c, the derivative of plus c goes away. You get 1/2 times 1 over whatever is inside the logarithm, which is the y squared plus 1, times the derivative of the inside, which is 2y. The 2's cancel, you end up with y over y squared plus 1, and that's, of course, what it should be. What's next? Compute the integral of the cotangent? Well, there's no substitution in there whatsoever. But what we realize is the cotangent is cosine of x over sine of x. So when trig functions are involved in integration, often it is best to use some trigonometric identities that bring things back to the fundamental trigonometric functions, cosine and sine. And now here, well, remember, when you've got a denominator, it can't hurt to try substituting the denominator. So we said u equals sine x, du dx is cosine x, dx is du over cosine x. That means the integral of the cotangent is the integral of cosine x over sine x dx, which is the integral of cosine x over u du over cosine x. The cosines cancel, so that's the integral of 1 over u du, which ends up being ln u plus c, and we back substitute, we get ln of sine of x plus c, and it turns out that that really is what it is, because when we differentiate, we get 1 over what's inside the logarithm times the derivative of what's inside the logarithm, 1 over sine x times cosine x, which is the cotangent of x, as we claimed, as we wanted. Okay, compute the integral of sine squared of x dx. Well, that's a composition, that's correct, because the sine function is plugged into the square, into the function z squared, if you will. But if we substituted u equals sine of x, we'd realize that there's nothing to cancel that cosine that we get from replacing the dx with du over cosine x. So this one doesn't work out like a direct substitution, but as I said before, when we work with trig functions, trig identities come back big time, and the one that comes back here is that sine squared of x is actually 1/2 1 minus cosine 2x. That is one of those double angle identities that you may have seen in trigonometry, that you should have seen in trigonometry. And if you don't remember it, it may well be because, well, the main reason why we teach those things is because we need them in something like this, and it's kind of hard to listen to someone saying, well, remember this, you may need it a year from now. There's a lot of things that people told me that I might need a year from now and that I probably will forget or have forgotten a year afterwards. Nonetheless, it is needed here. Without it, we really cannot proceed. But now that we've got that, we also see that we've got a composition. We've got a 2x in here, but that's a very quick substitution. U equals 2x, du dx equals 2, dx equals du over 2, and now we can work things out. The integral of sine squared x is the integral of 1/2 1 minus cosine 2x. The integral breaks up. It's the 1/2 comes out. It's 1/2 integral of 1 dx minus integral cosine 2x dx, and that's where we're using the substitution, of course. This is 1/2 integral of 1 dx is x. The other one is the integral cosine u du over 2. Note that even though we're mixing here, we're not mixing the variables in the same integral, so I would consider this, if not totally clean, then at least reasonably clean. We just have to make sure we keep track of not mixing u's with x's in the same integral. That gives us 1/2 x minus 1/2 sine u plus c, because the integral of cosine u is sine u, and then we back substitute the u. We end up with 1/2 x minus 1/2 sine 2x plus c, and again, always double check, take the derivative of this, and you end up with 1/2, which is on the outside, of course. Derivative of x is 1. The derivative of 1/2 sine 2x is cosine 2x times 2 times the 1/2, so the 2 times 1/2 goes away. We end up with 1 minus cosine 2x, and then we have to remember the trig identity. This really is sine squared x, as it should be, and again, we've solved the problem correctly. Well, another one. This one doesn't actually look as bad as the other ones. We've got an x minus 4 inside it, and a function that raises stuff to the 2/5, so we probably have to take u equals x minus 4. Okay, so du dx is equal to 1, dx is equal to du, and that feels kind of weird, because in all the previous examples, the extra term that we got when we replaced the dx with du over something helped us to cancel something, and that's not happening here. So does this really lead to success? Well, it does, because we can still get rid of the x, and x is equal to u plus 4, and that really is the key to this problem. So sometimes if you just have something linear inside an ugly function and then other stuff on the outside, you sometimes also just solve for x in terms of u and replace the x. So that is what happens here. The integral x times x minus 4 quantity to the 2/5. That's the integral of x times u to the 2/5 du, which is the integral of u plus 4 u to the 2/5 du. And now we just multiply things out, and this is the integral of u to the 7/5 plus 4 times u to the 2/5. And you can see at this stage why the substitution is advantageous. It allowed us to take a difference or a sum. Well, a difference is just a sum with a negative second sum end, right? It allows us to take the sum that is inside the function and turn it into a sum that is outside the function. These things we can now integrate. This we could not. So this becomes, well, 7/5 plus 1 is 12/5, so we end up with 5 over 12 u to the 12/5. 2/5 plus 1 is 7/5, so we end up with 5 over 7 times 4, which is 20 over 7 u to the 7/5, right, plus c. And then we back substitute, so this is 5 over 12 x minus 4 to the 12/5 plus 20 over 7 x minus 4 to the 7/5 plus c. And well, now we can still double check. It's going to be a bit tedious, but with something like this, it is easy to lose some of the constants, so it's a good idea to double check. Take the derivative. Well, we keep the 5/12, we get a 12/5 from the exponent, x minus 4 to the 12/5 minus 1, which is 7/5. 20 over 7 we keep, we get a 7/5, which is the exponent coming down. X minus 4 to the 7/5 minus 1, which is 2/5. The derivative of the plus c is 0, of course. Then we see that this all cancels, and this turns out to be 4. So this is x minus 4 to the 7/5 plus 4 times x minus 4 to the 2/5. That's pretty close. What happened here is that, well, now this is not obviously the same thing, but we have an x minus 4 to the 2/5 in our original function, so we ought to factor that out. And if we do that, if we factor out an x minus 4 to the 2/5 from the first one, we keep an x minus 4, and from the second one we just keep the 4, and of course minus 4 plus 4 goes away. So we end up with x minus 4 to the 2/5 times x, which is exactly what we've got here. So again, we got it right. That is very reassuring. Finally, we also want to work with parameters in those integrals. Well, you've seen this motivation before. Basically, ultimately, we'll work with, just like we've seen with optimization problems and with all sorts of things with derivatives, ultimately, in physics, in the sciences, we work with stuff that involves a lot more than one variable, such as universal gas law or the van der Waals equation, or things like the frequency for the harmonic oscillator, or even the differential equation for the harmonic oscillator. As I said before, if those things don't speak to you quite yet, just realize that this is what lies ahead, and we can tackle these formulas better if we're used to working with parameters. In terms of working with numbers, I'd always rather work with pi than with all those digits. And parameters, we've seen that now also in the optimization. We get stuff that's applicable to more problems. And in more elementary terms, the graph of an arbitrary quadratic function is described by this formula. And we've also seen the optimization. If we optimize for an arbitrary fixed volume, we have a solution that is more versatile than if everything is given by numbers. And we've also seen in the past that just solving more problems without parameters really doesn't give us the training that we need to proceed. So that's what we would ultimately use computers for anyway. We would parameterize the problem and program it. And finally, we've also seen, for example, in the derivation of Snell's law, that you really do gain deeper insights by solving these harder problems. You just get that much more unscrupulous when it comes to something that has a lot of symbols in it, for example. It just doesn't bother you that much anymore. So we want to compute the integral of 1 over quantity x minus a raised to the nth. And how do we do that? Well, the substitution, since x minus a is plugged in here, is probably u equals x minus a. du dx equals 1, dx is equal to du, so it shouldn't be that bad. But we really only wanted to get rid of that difference in the denominator anyway. We end up with the integral of 1 over x minus a to the n being the integral of u to the minus n, right? That's 1 over u to the n, which is u to the minus n. And that works out for n not equal to 1 being 1 over 1 minus n u to the 1 minus n, right? Because you just add 1 to the exponent and multiply with the reciprocal of the exponent. And for n equals 1, we get u to the minus 1 here, and if we add 1 to that, we get 1 over 0. That doesn't work, but we remember that the antiderivative of u to the minus 1 is ln u, and so we get ln u plus c when this n is equal to 1. And that, of course, also somehow connects to that mistake that I made in the previous presentation. Well, if your exponent is in the denominator, then you have to worry about n equals 1, not about n equals minus 1. Either way, we do the back substitution, and this is the result. The antiderivative is 1 over 1 minus n x minus a to the 1 minus n plus c for n not equal 1, and ln x minus a plus c for n equal to 1. And that's already it. We've seen a lot of examples about substitution, but I've taken pretty good care. I think these examples contained all the various tricks that you can encounter in substitution, and with more experience in symbolic integration, with more experience in doing substitution, which you will get on the homework, for example, you will become more adept as to which trick, which trig identity, which kind of substitution, which kind of solving for x you have to use for what kind of integrals. But that only comes with practice, and well, that's what I want you to do now. I'm going to move on to integration by parts, and I'll see you there.